All right, welcome everyone. So what we're going to be doing today is we're doing electrochem notes. And the nice thing is that a lot of this is actually a review of what we've done at the beginning of the year. And so a big part of this is understanding redox. So let's first talk about what is electrochemistry. Well, the first part of it, the electro part, refers to one of the subatomic particles. Which one? The electron, okay? And so what we're really talking about is the chemistry of the electron and the movement of the electron. And the coolest thing about the electron is we know that we've heard of batteries and we've been using batteries ever since we were really young. And really, the function of a battery is all based on electrochemistry, okay? And so application-wise to our everyday lives, this is huge as far as how this works. But maybe we haven't really spoken too much about how does a battery work and how is it that these electrons are able to move and then we can get energy from that. And so that's what we're going to be talking about today. Is we're going to be talking about what a cell is and a cell's potential and how you can calculate that, how you can calculate how much energy, and what does it take to get it to stop? Why do batteries come to a point where they stop? And so we'll talk a little bit about that. So the first thing is redox, okay? And so we know redox, we've done the redox reactions. We said some of the big things are Leo says Ger is good to know, and Dr. Yuo. So let's go over those real quick. What's Leo says Ger? Well, by definition, it defines oxidation and reduction. So what is Leo? Lose electrons means that it's oxidized. What's Ger? Gain electrons, reduce. Perfect, so that's right there. So lose electrons, oxidize, gain electrons, reduce. What is Dr. Yuo? Well, the doctor just means if the charge goes down, we call that reduced. And if the charge goes up, we call it oxidized. So if your charge goes down, it's reduced. If it's up, it's oxidized. What does that mean? If you're looking at a reaction, how can you figure out one or the other? So what you do is, you can look at a reaction, and the first thing that you want to do is you first want to write down all of your oxidation numbers. And we know how to do that. We've been doing that for a while. So you write down your oxidation numbers for everything on here, realizing that things that are in their standard state have an oxidation number of 0. In other words, they have no charge. So if you get something like a piece of solid magnesium or a piece of solid copper, or maybe you have hydrogen gas, H2 gas, those are all values of 0, okay? And so the oxidation number or the charge of it is 0, meaning that it hasn't lost or gained any electrons. But in this case here, we can figure out what the oxidation numbers are. Typically what you do is you look at the one on the right, and that's the one that is going to be the one that's gaining the electron, typically. Because you look at both of these and you're like, wait a minute, carbon and nitrogen, those are both nonmetals. Those will be both considered to be elements that would gain electrons. But one of them has to be positive, okay? So that it balances out. So what you basically do, for example, on Cn minus, is you would say that it has to equal a -1. And so if you say x plus -3 equals -1, the question is, what's x? And so then you would just say that x is equal to a +2. That's how you figure out what the charges are of each one of those. Once you have that down, and oxygen in all of these molecules, if it's in a compound, if it's O2 gas, it's 0. But if it's in a compound, oxygen has what charge? What have we've been using since the beginning of the year? -2. But if you look at the periodic table, oxygen can also be -1. There's only one situation where it's -1. It's when it's in what? Anybody remember this? Starts with a P? Peroxides. Awesome. If it's H2O2, it has a -1 charge. Otherwise, you're going to do oxygen as a -2. Okay? So the rest of them are pretty easy. It's based on whatever the charge is. If you get a metal that has a variable charge, look at the nonmetal. Okay? And that's going to tell you what the metal's charge is. All right. Once you do that and you figure out your charges, you're going to check to see if the chart changes. You'll get one Leo and one Ger, or one doctor and one Yuo. You will not have a doctor without a Yuo. In other words, you're not going to lose electrons and not have a place where electrons were gained. Okay? So the electrons that are lost have to be gained somewhere else. All right? So you're not going to have one without the other. So I look at the carbon here. We can see that the carbon goes from a 2 to a 4. So that means that the charge went up. And the charge, if it goes up, then what is the guy's name? Dr. Yuo. Then that means it's oxidized. Okay? And you would be talking about the reactant. You would say this reactant is oxidized. All right? Well, if this one's oxidized, without even looking at this one, you would say that this one must be reduced. This one, nothing's changing. If you look at the H, it's still a +1, and you look at the O, it's still a -2, so that one's not on any of them. It's still a -2, so the oxygen's not changing, so it would have to be the MnO4 that is the one that's changing, or the permanganate ion. So in this case, again, if you look, it's 7 going down to 4, so that would be your down reduced. Or a question may ask you, is it losing electrons or is it gaining electrons? So in this case here, if our charge is going up, then that means that it's losing electrons. And why would your charge be going up if you're losing electrons? Perfect, because we know electrons are negative. Okay, so if you lose negativity, it makes it more positive. Okay, so but sometimes you get confused. So that's why I like Dr. Yuo. It makes it really easy to just say, is my charge going up or is my charge going down? And that's a nice way of doing that. Okay, once you do that, then you always want to make sure that you balance your electrons, because again, you can't just lose a certain number of electrons and not gain an equal amount. The amount that's being lost has to equal the amount that's being gained. So in this case here, we're going to be gaining 3 electrons, and in this case here, we're going to be losing 2 electrons. Well, that doesn't make sense. You can't gain 3 and lose 2. That's not balanced. In a battery, it has to work out where the electrons lost are equal to the ones gained. So what we do is, we try to figure out the least common multiple between them. And in this case, you would say 3 times 2 is 6, and 3 times 2 is 6. Okay, and so once you have the balanced half reactions, the numbers that you put in, so for example, in this case, you could say that that's going to be a 6, which I do over there, but that's going to be a 6, that's going to be a 2, and then that's going to be a 2. So you're just going to distribute that through. And that's going to be a 3 and a 3, and then that would be a 6. So now they're on opposite sides. Your 6 electrons are what are transferred in this battery or in this cell, because sometimes you'll be asked that. How many electrons are transferred? It's not 3 and it's not 2, it would be 6, okay? And so once you have those numbers, that's what you put in front of the coefficients there. Now, in this case here, typically, whatever the equation is what they give you and you're done. But this solution, it says that it's a basic solution. Sometimes it'll say it's acidic. If it's basic, you're going to add 2 things. You're going to add water to one side, and then what do we know bases by the Arrhenius definition? Bases release what into solutions? OH minus. And you're going to put OH minus on the other side. Now, I do it as a trial and error. You have to look at the equation and try to figure it out, or just try it. Just throw your water and your hydroxide in on both sides and see which one works. If you don't get it to work right away as far as balancing it, then switch them, and it should work pretty quickly, okay? If it's an acidic solution, guess what you use? Water, and what do acids release? H plus. Perfect. And so same thing. You would do H2O and then H plus on the other side, and you just try it to see. Sometimes it's a giveaway where you might look and say, okay, I don't have hydrogen on the other side, or something like that, where there's a certain element that you don't have, then sometimes that helps to try to figure out which side each one is on. All right, and that's basically it for redox. So now let's talk about these electrochemical cells. Electrochemical cells are used to produce electricity. So that's what we're talking about here, like the battery in your calculator or your car. Electromotive force, EMF, or cell potential are the terms that they use to describe the potential difference between the electrodes in a cell. What causes the electrons to flow from anode to cathode? How is it that the electrons flow? Similar to other spontaneous chemical reactions, it's all based on, what do you think it's based on? Starts with an E. It's all based on energy. That's it. It's all based on the energy. That's it. A voltaic or a galvanic cell is a device that forces what transfer? What's moving again? Electron. Perfect. Electron transfer to take place through an external pathway rather than directly between reactants. So I'm going to show you how the cell works. We'll do a simulation. There's a really cool demo that we're going to use. Each half cell in a voltaic cell has a different potential energy. When the electrodes are connected by a circuit, the electrons flow. And so once you get the flowing, then you can produce this energy. It says the potential difference between electrodes is measured in volts. And so I know a lot of you are in physics right now, and so all a volt is it's a joule per coulomb. We'll talk about what the coulomb is in just a little bit too. This is called the electromotive force. It's also written as E cell. Okay, it's also written as E cell. It's also written as EMF, or it's also called the cell potential. So those are 3 different things that you can be asked. It'll say, what's the E cell, what's the EMF, or what's the cell potential. All of those refer to the same thing. Under standard conditions at 25 degrees Celsius, 1 atm and 1 molar concentrations, EMF is called the standard EMF, and so that's why you get this standard, that 0 right there. That's the E cell. E cell is very simple. It's simply take what your EMF is at the oxidation point and add it to the reduction point, and you've got it, okay? It's a lot like Hess's law, but it's actually easier, okay? Because well, let's read through. So it says, half-cell reactions are assigned EMF values in a chart, and it's called the standard electrode potentials in water at 25 degrees Celsius. It's important to note that these are all reduction potentials. We're going to take a look at a chart in a second here. The oxidation potential, what do you think? If it's giving you a chart of only reductions, what do you think oxidation is? Opposite. Perfect. It is simply opposite in sign. That's all it is. You just switch the sign and you've got oxidation instead of reduction. So let's take a look at our reduction chart and check to see what these values are. This is really important. An important thing to remember is the potential does not change, circle the word not, it does not change with the change in moles. In other words, you can have your reaction times 2, you can have your reaction times 3. If your voltage is 1.67 volts, for example, so let's say times 1 is 1.67 volts, it's still 1.67 volts. Even if you multiply by 3, it's still 1.67 volts. The only way that it's going to change is if you flip it, okay? If you reverse your reaction, reduction becomes oxidation and your sign flips. That's the only thing. So let's take a look at the reduction chart and let's try to see if we can find zinc, okay? So we're looking for zinc going from a +2 to a solid, and so let's take a look at this chart. And so we're going to scroll down, and this is not done alphabetically, by the way. How is this organized? Well, you can see that the most positive numbers are on top, and the most negative numbers are on the bottom. This is actually organized according to strength. Strength of what? How good it can be, how well it can be what? What is this called? Reduced. Awesome. This is a reduction potential chart. So this one at the top has the highest reduction potential. In other words, it will, if you put it in with anything, that's the one that's going to be reduced. Guess what the other one would be then? Oxidized. By nature, that's how it's going to work, okay? So in this case here, we can look and we can try to see if we can find zinc, and I see zinc right here, down here on the chart. And it's in the same exact order. It says zinc 2+ plus 2 electrons yield zinc solid. And there's a reduction potential. It says negative 0.76. So let's just write that down. It says that it's a negative 0.76 volts, and the whole chart is in volts. So now look at this reaction right under it. How is that different? How is this one different from the other one? It's opposite. Perfect. So instead of zinc solid being on the product side, now it's on the reactant side, which means in this case you're going from a 0 to a +2. And so if you're going from 0 to 2, your charge is going up, which means UO, oxidized. It's the opposite of reduction anyway, okay? So what do you think the value would be here? Positive 0.76. Awesome. Now try this. What do you think the answer is based on what I told you? Let's see how many people were listening. What's the answer? Everybody, 1, 2, 3. 0.76. Awesome. Positive 0.76 volts. If you multiply by 2, divide by 2, times 3, it doesn't matter. It does not change your voltage, okay? So the more positive the E value, the blank the tendency for the reaction to proceed in that direction, what do you think? The higher, yep, the more likely or the greater the tendency for it to proceed in that direction. So what that means is, and I'll probably indicate this later on, you know when we were talking about spontaneity when we were doing thermochem, what that means is, and we said, anybody remember the saying, Sarah something? Sarah eats gross ham. Good. Sarah eats gross ham. And so what we said was, your E cell, Sarah eating, remember those were positive, and gross ham was negative. You actually want a positive E cell value, and that does determine spontaneity, okay? Delta G and delta E, both of those will tell you that a reaction is spontaneous. And spontaneous just means it's going to proceed in that direction without the addition of what? Outside energy. Perfect. Okay. So which of the following is the strongest oxidizing agent? Now, they removed this from the AP. They're not going to be using agent, okay? So what it could say is the strongest, has the strongest or the highest or the greatest reduction potential. It's really easy. The agent is actually the opposite, okay? So if you do come across this sometime in the future, the agent's just the opposite. I don't know why they decided to get rid of it. Okay, so we want to know which one has the highest reduction potential. Cl2, MnO4 minus in a basic solution, or Fe2 plus. All right, so based on these three values here, and sometimes you have to look at a different chart depending, usually you'll be given a chart that has all of them. Which one's the highest? Cl2, awesome. And then which one comes next? Then which one comes next? Fe2 plus. Fe2 plus. And then which one? MnO4. All right. Okay, good. So now, if they asked for oxidation, oxidation would just be the opposite. All right? Oxidation would be the opposite because when you flip it, it's the one that would be the highest after you flip those signs, after you switch your signs. Okay, when working with galvanic and voltaic cells, remember the following. Oxidation occurs at the anode and reduction occurs at the cathode. Really easy to remember. All you're going to do is you're going to think, there's a red cat over on that side of the room, and there's an ox on that side of the room, and the ox is mad and the ox is hungry, okay? Do you run toward the ox? No, you're like, an ox, and then you start running as fast as you can to go toward the red cat. Oh, pretty red cat, okay? So, everybody, the direction that the electrons flow are, you see an ox, you see a red cat, which way do you go? Toward the red cat. Awesome. Okay, so in this case here, and the words are going to help in a whole bunch of different ways, so I'm going to show you how this makes a difference. Electrons flow from oxidation to reduction, or anode to cathode. And so you can remember that anode, an, ox, oxidation, and then red just stands for reduction, and cat would stand for cathode. Okay? So you have the two different, typically what they do is the anode and the cathode are metal pieces that were put into the solution. So they'll call one the anode and one the cathode. So electrons flow away from the ox toward the red cat, and memorize this now. The electrode that gains in mass is the one that starts as an ion and ends up as a solid. For example, if we look up at a reaction that we had earlier with the zinc, for example, and it said zinc plus 2 electrons yield zinc solid, what's happening is the zinc ion is gaining 2 electrons and it's becoming zinc solid, which means you're getting more and more solid, and so what's going to happen to your mass? It's going to increase. It's going to go up, okay? So it says electrode that loses mass is instead, if it loses mass, then it must start as a solid and turn into an ion. Perfect. It starts as a solid and ends up as an ion. Okay, and so that one, the solid's going to come off and turn into an ion, so your mass of either your anode or your cathode would be decreasing. The two half reactions in a voltaic cell are, and so we're given 2 of these half reactions, and it'll be done this way on the exam as well. There is no reduction chart that's given to you, so they'll just put it right into the problem. Which reaction occurs at the anode? Well, let's figure this out. So if these are the 2 half reactions, and I'm seeing that one has the electrons on the right and one has the electrons on the left, then I know that it was written correctly. One's a reduction and one's an oxidation. So what's this one? Well, it's going from 0 to 2, so the charge is going up, so that's my UO. So then what would you say if it's your UO? Well, then this one's got to be my doctor, right? So if that's my UO, we call this, is it anox or red cat? Which one is the top one? Anox. Awesome. This is anox, which means this one must be my red cat. Okay. Okay, yep, that's the anode. The top one's the anode, and the bottom one must be the cathode. Which reaction occurs at the anode? So then it must be the zinc that's occurring that is my anode. Typically, it's a solid. It's usually a solid, a metal plate. But in this case here, it's got to be the ClO3 minus that's acting as my cathode. Okay, so it's the other one. Which electrode is consumed in the cell reaction? When they say consumed, they're saying that it's basically losing in mass. Which one's being eaten up or consumed in this case?
Zinc.
Why the zinc? You're right. Why the zinc? Because it's turning into an ion. Solid is turning into an ion. Okay? So that means it's being consumed. Which electrode is positive? So if it's the positive electrode, then go back to what we learned before. Remember when we did an ion and cation? It's similar. So anode and cathode. Which one was positive? Cation. So the cathode is the one that is the positive. And so which one's the cathode? The ClO3 minus. Okay. I will tell you that in electrolysis, things work backwards. So your anode is actually your cathode. It's reversed. The one that's negative is actually your cathode, and the one that's positive is your anode. We'll talk a little bit about electrolysis later, but just so you know. How many electrons are transferred? Well, this one says 2, and this one says 6. What's your least common multiple between them? 6, because you can do 2 times 3 and then just have 6 times 1. So 6 would be your number of electrons transferred. You can just multiply the top one by 3. All right. Galvanic and voltaic cells. You have a blank in a solution of its ion on both sides. What did I say? You would have the plate would be typically what? Made of what? A metal. Awesome. So you have a metal in a solution of of its own ion on both sides of the cell. And the potential difference between the two sides is what causes the current to flow. This is really important. So the potential difference between your two sides is what causes the current to flow. So one half of the cell is the reduction, and the other half must be the oxidation. So one side's reduction, one side is oxidation. And what you want to do is, you can basically tell just from using the chart, because in nature, the way that it happens is the reaction will tend to be spontaneous, and problems will ask you, for a spontaneous reaction, what is it? Sometimes they'll give you problems and they'll ask you, is the following spontaneous as written? Well, you would want to check to see what your E cell value is. If it's positive, yes, it's spontaneous. If you work it out in the direction as it's written and it's negative, then that's non-spontaneous. Doing the reverse would be spontaneous then, okay? So one thing that we need to do before we do this is we need to talk about what is called the salt bridge. So what we said was, the coolest thing about this is it actually takes the electrons and gets the electrons to flow outside, not inside, not within. The electrons actually flow outside. What this thing is here is your salt bridge, okay? And the salt bridge will look different. I want you to see what it looks like in the demonstration because that's more like how it looks too. And so it says it's an electrolyte solution, some type of salt. And remember, typically salt is, when we think of salt, we just think of what? When I say salt, you think NaCl, right? When they say salt, they're talking about something that's going to ionize, okay? And so as long as it drops ions, then that's going to be a salt. And the coolest thing about this is if you don't have a salt bridge, your battery will stop functioning almost immediately. The salt bridge is what actually keeps it going for a longer period of time. And here's how it works. So it says, by definition, and I've seen this as multiple choice as questions to say, like, just what is a salt bridge? All it does is it maintains electrical neutrality. It maintains electrical neutrality. It keeps your solution neutral so that it can keep on going. Your reaction can keep on going. What it does is it provides negative ions and positive ions to both sides of your battery, depending on what side needs it. And it happens naturally. It's not like I'm going to go in and set it up and say, hey, electrons, I want you to go that way, and hey, positive ions, I want you to go that way. It doesn't work that way. It naturally just happens, okay? And so what happens is, if you have too much positive on one side, the salt bridge is going to release negatives into there. Well, why does that happen? What do you know about positives and negatives? They're attracted. And so what happens is if you have too many positives on one side, it naturally will release negatives. Or if you have too many negatives, it will naturally release positives. And the nice thing about a salt bridge is that it completely ionizes, and so it will just start releasing Na pluses and NO3 minuses, and they take off in opposite directions depending on where there's a greater concentration of the opposite ion, okay? So it's pretty simple to understand here. It says, use your table to select the two half reactions between the two ions and the metals in the electrochem cell. And so what are the two half reactions? Well, what we're going to have to do on the second step, we're going to merge the first and the second step into one. The second step says you're going to have to reverse one of the reactions so that you have an oxidation and a reduction. Let's just do it right in the beginning, okay? So what we're going to do is we're going to try to choose the one that is going to be reduced, that's higher on the chart. The one that's lower on the chart, we're going to flip it and make that the oxidation, because you can't have two reductions, okay? One has to be an oxidation. It says to obtain an E cell, a positive E cell, you always want to reverse the one that's more negative or the one that's lower on the chart, okay? So let's take a look. Let's find nickel, and the question may be, is it nickel plus 2 or is it nickel plus 3? K only has a +1 charge, but you're going to look at the solution to be able to tell. Nitrate has a -1 charge, and if there are two of them, what must nickel's charge be? A +2, okay? So we're going to find the one that's nickel plus 2, because sometimes they'll give you a chart, it'll be minimized. They'll only give you 4 of them, and they may give you an option of choosing one or the other. So let's take a look at the chart. We're looking for nickel. Okay, so we figured out that the nickel was a -0.25 and the potassium was -2.92. If that's the case, the one that's lower down on the chart, that's the one that we need to flip. That's the one we need to reverse and make our oxidation point. So this one's going to be our reduction and this one's going to be our oxidation. Okay, so let's first write our reduction one, which is the nickel one. And so that one we're going to write exactly the way that it is on the chart. And on the chart it says Ni2 plus 2 electrons yields Ni solid. Awesome. And the value was -0.25. This one we're going to flip. So instead, the oxidation one we're going to do is the potassium. So we're going to flip it. So we're going to make it K solid, then our arrow, and we're going to get K plus 1 electron. And so what happens to the value of it? It's positive now. So now we're going to flip it and make it a positive 2.92. What you basically want is you want these two, when you add them, you want the highest positive number for a spontaneous reaction. Okay? So now all I'm going to do is I'm going to add these together. Well, you might look at this and say, wait a minute, this one, what do you have to do to this reaction? Multiply by 2. But what did we say about this? It doesn't change. So even though we're multiplying it by 2, it actually does not change your voltage. Your voltage is still the same. Okay? So now let's come down. Number 2, we already did that. So check this off. We already did that above. And now number 3 says, to balance the electrons, multiply the potassium equation by 2. Remember, don't multiply the voltage. We know to do that. All right. Well, when we do that, we're not going to do this all over again because we already wrote them properly. All we're going to do is we're going to add this together to get our final equation, because sometimes they ask you, what is the final equation? Okay? Well, if we put a 2 in there, and we put a 2 in there, and that one changes to a 2, then what happens is our 2's cancel out, so we're left with Ni2 plus, so it's supposed to be a plus, and then down here we have plus 2K solid, and that's it on this side because our electrons are going to cancel out with each other. Yields, on this side we've got nickel solid plus the 2K plus, and this is an ion, so we're going to just leave it as aqueous. And now the question is, what's this value? Okay. So what do we get when we add 2.92 and -0.25? We get 2.67? 2.67, and the units are volts. Okay? So that's going to be our E cell for this reaction. It is the standard E cell because we got all of our values from the chart, and so that is called the standard E cell value, and all you're going to do is just add those up and you're all set. So now the question is asking, which one occurred at the anode and which one's at the cathode? So what did we say? We said if it's R, then it's red cat, and this one is an ox. So I like to write that down. Okay, write down as much as you can. It's going to help you when you go to fill things in so you're not making a mistake. So which one's the anode?
The K.
The K. And it is, typically it's the metal piece that's the anode. So we're going to say it's the solid piece of potassium. So then what's the cathode? The cat is The nickel solid. So it doesn't matter what side it's on, it's typically the solid, the metal. Which electrode is consumed? In other words, which one is losing mass? When they say consumed, it's like getting eaten up. Okay, so it's losing mass. So which one is losing in mass? What did we say? The one that's becoming that solid going to an ion is? Okay, solid. Very good. And now which electrode is positive? What did we say? Which one's positive? The anode or the cathode? The cathode. So which one's the cathode? The Ni. And the last question is, how many electrons are transferred? 2. Perfect. 2 electrons are being transferred. All right, let's take a break. Okay, so next what we're going to be talking about is spontaneity. And we've already talked about this, so this is nice because it's kind of reviewing a little bit too. It says a spontaneous process is one that will proceed in the direction written without the addition of outside energy. It indicates nothing about how long it takes. It does not tell you anything about the kinetics, so keep that in mind. So a multiple choice question would say, the following reaction is spontaneous. Which of the following are true? And then it'll say something to the effect of the reaction happens quickly. It doesn't tell you anything about that, okay? So free energy, or delta G, we talked about before when we were doing thermal, and that measures spontaneity. When delta G is negative, the reaction is spontaneous. Also, if you have a positive E cell, so when your E cell is positive, that also means that it's spontaneous, that you have a spontaneous reaction, okay? And again, that means that your reaction is going to proceed and move toward the products, from reactants toward products in that direction, without adding any outside energy. So delta G is equal to negative N Fe is the equation that relates delta G to E. Delta G is simply Gibbs free energy, standard Gibbs free energy. And what units did we use when we were doing delta G? So on our thermo chart, it was measured in kilojoules per mole. Perfect, kilojoules per mole. Remember, it was delta S that was in joules per mole Kelvin, and we had to switch that to kilojoules. We had to shift our decimal 3 loops back. What do you think N is? Well, N is the same as when we were doing N before. It's just simply the moles. Perfect. But this is the moles of electrons transferred. Okay, so it's not just moles. It's your moles of electrons. So you know how we figured out like 2 electrons? You would say 2 moles of electrons. That's what goes there. And Faraday's constant. Faraday's constant, I've always known as 96,500. But on the new equation sheet, they actually give you 5 sig figs. They make it 96,485 coulombs per mole of electron. Okay? So 96,485 coulombs per mole of electrons transferred. Okay? And so what ends up happening is you could get your kilojoules per mole for your delta G. As long as you know what these units are, everything's going to cancel out. You should end up with kilojoules per mole in that case for your delta G. If N and F are always positive and E is positive, well, if that's the case, these are always going to be positive numbers. There's a negative in front, but when you say mole of electrons, you're just going to say 2 moles of electrons. So it already does the negative for you, okay? So you're going to say positive, positive, and if your E cell is positive, then what's your delta G? Negative. Why is it negative? Because there's a negative sign in front of a bunch of positives, and that makes this negative. And we said that if delta G is negative, Sarah eats gross ham, then gross, negative, that makes it spontaneous. And that's why a positive E cell, or a negative delta G, just like we said here, would tell you you have a spontaneous reaction. If N and F are always positive, again, so if this is positive and this is positive here, and your E is negative, well, there's a negative in front of it in the equation, then what would your delta G be? Positive. And so then it's positive, and in that case, you have a non-spontaneous reaction. Okay, so that's how they got E and delta G to relate to one another. All right. Okay. So question 5 says, using the standard electrode potentials, and this was a question from your book, calculate delta G, the standard free energy change for this reaction. And they're asking you if it's spontaneous. If they ask you whether or not it's spontaneous, you are not going to do the flipping yourself. What you're going to do is you're going to look at your reactions, and you have to try to figure out how it would work so that based on, you know how we add up the reactions to equal our total reaction? We want to make sure that these 2 would add up to equal this reaction as written. And then we're going to try to tell if it's spontaneous. So I'm going to try to find one thing in this reaction line that appears here. Do you see something that appears in this reaction that also appears here? Good. On the top one first, though. Let's use the top one. The IO3 minus. I'm seeing this right there, and I'm seeing it right there. Okay. And so what do I need to do to that top reaction? Times it by 2 and flip it. It's on the wrong side. So I'm going to reverse this one, and I'm going to times it by 2. Okay. And then what about the other reaction? This one down here. What about that? The CO2 plus. Awesome. And where do you see that? Same side. So what do you need to do to this one? Times 5. But remember, if you multiply and divide, you do not change your voltage. Your voltage remains the same. You're only multiplying and dividing your reaction so that you can get your total overall reaction. That's the only reason why you would do that. Okay? Sometimes they'll ask you, they'll say, write the final reaction for this battery or for this cell. So if we needed to do that, what we would do is we would flip that top line and then we would multiply everything by 2. So if we flip it and multiply it by 2, we're going to get I2 solid plus 6H2O liquid yields, then this is times 2, 2IO3 minus, plus 6 times 2 is 12H plus 5 times 2 is 10 electrons. But again, our E cell, the only thing that changes is we reversed it. So what's different about that? It's negative 1.195 volts. Awesome. And then the second line stays exactly the same. We just multiply by 5. So 5 Cu2 plus 10 electrons yields 5 copper solids. And this one we're not changing. It's just going to be positive 0.337 volts. All right, and then what you want to do is you want to add these up to get your overall. Well, the 10 electrons are gone. And basically, all you're going to do is you're going to just rewrite everything down here. Okay? And that's your overall final equation. So I'm assuming you know how to do that, so we could rewrite that just for the sake of time here. Now, what would you do to these numbers to figure out what your E cell is? Add them. Go ahead and add these. Negative 0.858 volts. And if this is your E cell, you don't want your E cell to be negative. You want it to be positive. So then is this spontaneous? No. This is non-spontaneous. But what they may do is they may also ask you to calculate delta G. Sure. So delta G is equal to negative N times F times E, and this equation is given to you on the chart. So let's just write down what our values are. Negative. How many electrons were transferred? 10 electrons. So this is our moles of electrons. Times F, which we said the number was 96485. 96485. And the units were coulombs per what? Mole of electrons. So our moles of electrons will cancel out right there. And we've got coulombs now. And the last thing is, what's our E cell? Our E cell is negative 0.858 volts. And so all you're going to do is you're going to multiply this together. 828. And the units actually end up being in kilojoules. Okay? The units end up being in kilojoules. And it's positive delta G, which again, a positive delta G tells us that our reaction is non-spontaneous. Okay, so this is voltage and equilibrium relationships, and we're going to be talking about what is called the Nernst equation. So the standard EMF is related to the equilibrium constant to K. And we know basics about K. We know that if K is greater than 1, then that means that you're favoring the products. And if K is less than 1, everybody, you're favoring reactants. Okay? And so we know that that's basically what K tells you. So, and Lechat's principle still applies. Remember, Lechat's is basically you add to one side, it favors the opposite side. You take something away, you put it back on the same side. If it's pressure, we did the more is less and less is more. You check to see how many moles are on each side. You ignore solids and liquids, so you do gases and aqueous substances. So it says the standard EMF generated by a cell increases as your equilibrium constant increases and vice versa. Why? Well, if your EMF is increasing, and you need to make sure you understand this conceptually, okay? So as your cell potential increases, your reaction's proceeding toward what? In what direction? Reactants to products. And if you're favoring the products, then what do you know about K? K is always going to be greater than 1. Perfect, that's it, okay? And so it says this means if K increases, you're favoring the products. Okay, that's it. And so your cell potential increases. And there are a couple of different equations that are on here. Some are you at 25 degrees Celsius? What happens if you're at a different temperature? What happens if you're putting in random concentrations versus what happens if you're at equilibrium? Remember, the only difference between Q and K is Q is random. K is you're at equilibrium, okay? And so what is K? Well, K or Q is simply equal to your concentration of your products over the concentration of your reactants. That's it. So we're given these values. Again, we're going to use 96485 for coulombs per mole of electrons. I do like writing moles of electrons instead of just moles. That way you don't get confused. Okay, so it is moles of electrons. If you're trying to cancel things out, it's going to really help you make a difference. So we said positive E, your K is greater than 1, you're favoring the products. In this case, your delta G would be negative. Okay? If your E is negative, then your delta G is actually positive, and this would be a non-spontaneous reaction, meaning your reaction is going backwards toward the reactants. The reverse of it would be spontaneous. Okay? So this is non-spontaneous. This one is spontaneous. Okay? So this one here would be our spontaneous reaction. They're giving us a reaction, and they're giving us the E cell value. This is the standard cell value. And the question says, the voltage of 0.48 is true if the standard cell concentration of ions is 1 molar. So as long as you have 1 molar concentrations, then 0.48 is what you get. What is the cell voltage if the concentrations instead are 0.5 and 1.5 molar? What should happen to the voltage if the concentration of the products are more than the reactants? Well, if you get more products than you do reactants, then what's going to happen to your reaction? If you have too much on your product side, then what's going to happen? It's going to go backwards. And so your reaction, your voltage then, should decrease because you're going to favor the reactants. All right, so let's write this equation down. And in this case, we're trying to find our E cell, the cell voltage, and we're given our E cell, our standard. We are at 25 degrees Celsius, and so since we're at, or it doesn't even say, we're going to assume that it's at 25 degrees Celsius. They're not changing the temperature. So this one is if you're at 25, that's using K, so we don't want to use K, we want Q because we're at random concentrations. So we're going to use this one here. So we're going to say our E cell is equal to the standard E cell, we can write down the equation first, standard E cell minus 0.0592 over N times the log of Q. All right, so we know our E cell, they tell us that it's 0.48 volts minus 0.0592 over our moles. And so the question is, how many moles are being transferred in this case? Well, it's not too hard to figure out. You can basically check to see, in this case, aluminum is going from 0 to 3. And so we have 0 to 3, but times 2. And manganese is going from 2 to 0, but that one's times what? Times 3. So guess how many electrons are being transferred? 6. Okay? So we know that we've got 6 electrons, 6 moles of electrons that are being transferred, times the log of Q. And the question is, how are we supposed to figure out Q? Well, we know it's just products over reactants. Why are they only giving us 2 values? Why are they only giving us the 0.5 and the 1.5 molar? Because the other ones are solids. And remember, you do not include the solids when you're doing that. So the log of Q simply is the concentration of aluminum. Remember, it's Al3+, but what do we have to do to it? Squared, divided by the concentration of the Mn2+, and this one we're going to cube. So Q or K is equal to this, and so we're going to plug in the numbers they gave us. So it's 1.5 squared divided by the Mn2+, which is 0.50. So when we divide this, we end up getting 18, and so this is the log of 18. And just to speed this up here, once we do that, then what we can do is we can say we end up getting 0.48 minus 0.012. And so now I can just subtract that, and what we end up getting is 0.47 volts. Did it change by a lot? No, but it did decrease slightly. So they could really just have this as a conceptual problem to say, what happens to it? That's a very valid problem to say, what happens to the voltage if you're favoring the products, okay? And so we know that the voltage should be decreasing. And then this last problem here, it gives you the reaction again, and it gives you your E cell, and we're being given these two values, and it just asks for the cell voltage. Again, same thing. Let's just do this conceptually. What should happen to the voltage if the concentration of your products are less? If you're decreasing on your product side, what should happen? You're going to favor the products, right? If there's less of this, you're going to favor your products, and so what do we expect to happen? If you're favoring the products, what do you expect to happen to your voltage? It should go up. Your voltage should increase, and so we should be favoring the products. All right, and that's basically it for electrochemistry.